In our last class, we discussed photoelectric effect. What is photoelectric effect? When light having suitable frequency is incident on a metal surface, it emits electrons, and those electrons are called photoelectrons. Today we will see how the classic electromagnetic theory tried to explain photoelectric effect, all the characteristic properties of photoelectric effect, and it fails. And later we will see how Einstein explains the characteristic properties of photoelectric effect using quantum theory. So let us start. In last class, we have noted few characteristic properties of photoelectric effect. One was photoelectric effect is instantaneous, which means as soon as the light is incident on the plate, metal plate, they start emitting electrons. So that is one of the property. Next one, we observe that when we increase or when we increase the intensity of light, the energy of the electrons coming out will remain the same. But the current, photocurrent will increase. Or when we increase the intensity of light, the photocurrent will increase, but the stopping potential at which the current stops will have no effect. This is second characteristic which we saw. And then we also saw that when we increase the frequency of the light, the kinetic energy of the photoelectrons increase, which means the stopping potential increase, but there is no effect on the current or current produced by photoelectrons. So these are the three important properties of photoelectric effect, or three important characteristics of photoelectric effect, which we observed yesterday. Now today we will try to explain how classical electromagnetic theory tried to solve these issues. So first of all, according to classical wave theory, some time is needed for the emission of electrons from a metal plate due to the fall of light on it. But experimentally, it is observed that there is no time lag. You know that according to classical electromagnetic theory, light is a form of wave. So if a wave is incident on a metal surface, the energy is falling on it continuously. So it takes some time for the electron to absorb enough amount of energy and get out of the metal surface. So according to classical electromagnetic theory, they expect a time lag between the fall of light and the ejection of electrons. But experimentally, it is observed that there is no such time lag. So classical electromagnetic theory fails to explain why photoelectric effect is instantaneous. Now let us look at the second point. According to classical wave theory, the photocurrent should increase with the intensity of light, and this agrees with the experimental observation. We know that intensity of a wave is the energy falling per second per unit surface area. So if the intensity of the light falling is more, there will be more energy falling on the metal surface. So more electrons will be able to absorb them and come out. So the photocurrent should definitely increase. So this agrees with the experimental observation. So classical electromagnetic theory have no issue in explaining the fact that as the intensity of light increases, the photocurrent increases. Now let us see the next point. According to classical wave theory, the kinetic energy of electron should depend on the intensity of light and not on the frequency. Because according to classical electromagnetic theory, intensity means the energy falling per unit area per unit time. So if there is more intensity of light, there will be more energy falling on the electrons. So the electrons ejected out will have more kinetic energy. So that was their expectation. They could not find any relation between the frequency of light and energy of the kinetic energy of the emitted electrons. So here again, classical electromagnetic theory fails to explain why the kinetic energy of electron or stopping potential of applied stopping potential is dependent on the frequency and not on the intensity of light. So here it fails to explain this point also, the dependence of kinetic energy of electrons on the frequency of light. Now, another concept, that is the concept of threshold frequency, the fact that if the light do not have a minimum frequency, it cannot cause photoelectric effect. That fact could not be explained by classical electromagnetic theory. So it fails to explain three things. One, why photoelectric effect is instantaneous. Second, why the kinetic energy of electrons depend upon the frequency of light and not on the intensity of light. And thirdly, why there is a threshold frequency. Why there is a minimum frequency below which photoelectric emission doesn't occur, even if the intensity of light is increased. So these 3 points, classical electromagnetic theory could not explain. Is this clear to you?
So
Is it?
can you explain the last one, the threshold part?
Threshold frequency means there is a minimum frequency below which photoelectric effect will not occur. For example, I am not telling the exact value of frequency of light. Uh, you can compare the red light and blue light. Which has more frequency?
Blue light.
Blue light has more frequency. If red light is incident on certain metals, no photoelectric effect occurs. But at the same time, if you are making blue light incident on it with the same intensity, then photoelectric effect occurs. So there is a minimum frequency below which photoelectric effect doesn't occur. That fact could not be explained by classical electromagnetic theory. Classical electromagnetic theory could not understand why there should be a minimum frequency for photoelectric effect to occur. Okay, so it could not explain. It could be explained only
But
by
it's a fact, right?
It's a fact. It is an experimentally observed fact. We saw that here, below a threshold frequency, no photoelectric effect occurs. Only if the frequency is above a threshold frequency, photoelectric effect occurs. It is an experimentally observed fact. But classical electromagnetic theory could not explain that. Later, Einstein will explain why it is so using quantum theory. So that's what we are going to see. Is that clear now?
Yes, teacher.
Okay. Now let us see how Einstein explained photoelectric effect applying quantum theory. In 1905, Albert Einstein explained photoelectric effect applying quantum theory, and he received the Nobel Prize in Physics for that in 1921. Note that Einstein didn't receive Nobel Prize for his discovery of relativity. He obtained Nobel Prize for explaining photoelectric effect applying quantum theory because it is an experimentally observed fact which could not be explained by existing physical theories. So that's why he received the Nobel Prize. Now let us see. We have already learned quantum theory, according to which light is a sum of separate quantum or photon, and each quantum or each photon will have an energy E is equal to h nu. Nu means frequency. You can also mention it as E is equal to hf, where F is frequency. So energy of each photon or each quantum or each small package of energy is equal to HF. Or if you write that in terms of wavelength, it is equal to hc by lambda, because c is the velocity of light or electromagnetic radiation, and frequency is velocity divided by wavelength. So this is the energy of each photon. And according to quantum theory, light is a sum of a lot of photons. So when light is incident on a metal surface, a number of photons are incident on a metal surface. Now, sum of the energy of a photon is used to overcome the binding force of the electron. We know that electrons in a metal are bound to the atoms in the metal, right? So metals are made of atoms, and each atom has electrons, protons, and neutrons. You know that. And the electrons are revolving around the nucleus, which contains protons and neutrons. So each electron is bound to that atom, is bound to the attractive power of the nucleus. So there should be some energy provided to the electron to overcome this binding force and come out. So when a photon is hit on an electron, some of its energy is given to the electron so that it can free itself from the binding force of the atom. So some energy is used to overcome the binding force of the electron to the atom. And this energy is called the work function. It is represented by the symbol phi. So phi is equal to HFO, where FO is the minimum frequency or the
The
threshold.
threshold one, right? Yeah.
Yes, threshold frequency. So it's the threshold frequency. So now you know that. See here, red light, as you told before, red light has less frequency. If red light is incident on the metal surface, no electrons are emitted. Why? It will not have enough energy, enough work function of this metal. Okay, suppose here the work function of the metal is 2 electron volt. Now suppose a photon having energy 1 electron volt is incident on the metal surface. So can it provide the electron enough energy to come out of the metal?
No.
No. So if the light has a minimum frequency, a particular frequency, for lesser frequency, no photoelectric emission occurs. Okay. Now suppose another light ray having a higher frequency. So a higher energy, suppose 2.16 electron volt is incident on the metal surface. So 2 electron volt is the work function. And what is remaining? 0.16 electron volt. It will appear as the kinetic energy of the electron. Okay. So only if the frequency of the incoming light is more than a particular value, which is called the threshold frequency, photoelectric effect will occur. So Einstein's idea of explaining it using quantum theory works perfectly, right? There is no doubt. So that is why there is a threshold frequency below which the photoelectric effect doesn't occur. Now see, suppose another photon having energy 3.5 electron volt is incident on this metal plate, which have a work function of 2 electron volt. So 2 electron volt is utilized to free the electron from the binding force of the metal, and the rest of the energy, which is 1.5 electron volt, will appear as the kinetic energy of the ejected electrons.
If
So
we give same amount of work function, I like if electron gives 2 electron volt, then there will be no work, right?
it will be different for different metals.
No,
Okay.
no. For this metal only, I'm saying that
Mhm.
if we give 2 electron volt to the
Mhm.
metal,
Yeah.
there
If
will be
we give
no work.
a 2 electron volt photon, the electron will be ejected, but it will not have enough kinetic energy to move.
Okay, like it will stay in that part only, right?
It will stay in that part. But we saw in the experimental arrangement that we can apply electric current, right? We can apply electric current. So if this plate is positive in nature, it will attract the electron, right?
No,
It
teacher, I
can,
didn't get this part.
what?
I didn't get this part. You said right, electron will attract something.
Yeah, I told that if we are applying a positive and electrical energy and a negative plate, so, and on the negative plate, the light is falling. So the positive plate will attract that electron which is free, right? So it may
That
move
one
to,
will attract, right?
hmm?
The negative will attract the positive, right?
Yeah, electron is negatively charged.
Yeah.
So if there is a nearby positive plate which is attracting the electron towards it, what happens? The electron can move, right?
Yeah, then it can
Ah,
pass.
then it will move away from the metal. Okay, but if you are giving energy only 2 electron volt, as you told, work function is 2 electron volt, so it's the minimum energy required to just free the electron from the metal surface, but it will not have enough kinetic energy to move out.
Yes, teacher, got it.
So Einstein, applying quantum theory, framed this equation. E, that is the energy of the photon, will be utilized to give the kinetic energy for the electron and also the work function. That is the minimum energy which is required to free the electron from the metal surface. So HF, that is the energy of the incoming photon, half mv maximum square, that is the maximum kinetic energy of the electron. V maximum is the maximum velocity of the electron, plus the work function, which we can represent as hf naught. What is h here? What is h here?
Planck's constant.
Planck's constant. And what is the value of Planck's constant?
6.36 into 10 raised to minus 34.
Yes, 6.63 into 10 raised to
6.
minus 6.63 into 10 raised to minus 34. So here again, see, this is the threshold frequency F naught. That is the minimum
There is
value of,
difference from others, right? Like the threshold frequency
yeah,
will be
threshold frequency will be different for different metals, because different metals will have different work function because they are made of different atoms. So how strong the electrons are bound in each atom will be different.
it depends. It's made of only metal. I mean, what
Metals.
is this? Metal. Only metal.
Yeah, only for metals.
Okay.
So different metals will have different work function. So therefore, different metals will require different threshold frequency, different minimum value of frequency. Sometimes a green light which can cause photoelectric effect in one metal, but it cannot cause in another metal which has a higher work function, and therefore it requires a higher frequency light. Sometimes some metals, even the visible region, they cannot cause photoelectric effect. There should be more frequency than the visible. So it's like that. So it depends upon the metal on which the light is falling. Now, as the number of photons increases, so this part explains the why there is a threshold frequency and why the kinetic energy of the electron depends upon the frequency. As the frequency increases, what happens? The energy of the photon is more. So it can provide more kinetic energy. So kinetic energy of the ejected electron depends on the frequency. So that part is also explained by this Einstein's equation. Now let us see how this explains the uh, relation of intensity. As the number of photons increases with the increase in intensity. According to quantum theory, intensity of light depends upon the number of photons emitted. So, as there is more photons, there will be more intensity of light. So, each photon can go and kick out an electron. So more intensity of light means more photons are coming. So more electrons are kicked out. So more electric current will pass. So as the number of photons increases with the increase in intensity, the photo current also increases. But frequency is being unchanged. The energy and the velocity of the photons will remain unchanged. That is why the photocurrent depends on the intensity of light, not on the frequency or the frequency of the light. Is that clear? And intensity can do nothing to the kinetic energy of the electrons, because it depends only upon the number of photons. If there are more photons, all of them have less energy. Will photoelectric effect occur? No. So even by increasing the intensity, we cannot increase the kinetic energy. It depends upon the energy of individual photons or the frequency of individual photons, not on the intensity of light. So Einstein's explanation of photoelectric effect applying quantum theory is also accounting for the relation between intensity of light and photocurrent. And why by increasing the intensity of light, the kinetic energy of the electrons is not increased. So is that clear to you? How he
Yeah.
explained the
Teacher,
relation? Yes.
what's the charge of photon? It's neutral, right?
Yeah, it's neutral. Photon is neutral. It's a
Okay.
radiation. Its
Yeah,
rest
radiation.
mass is zero and it is neutral. So it's just a package of energy, that's all. And this energy can be transferred to the electron, completely transferred to the
They
electron.
just replaced the electrons, right?
They are just absorbed by the electron. It's a bundle of energy. So the electron just absorb that bundle of energy. Now photons, here it comes, what just now I told. Photons collision with matter is elastic in nature. Do you remember what is meant by elastic collisions?
Yeah, where yeah,
Where
the no, yeah, I remember that where the kinetic energy is preserved, both kinetic
kinetic
and
energy is conserved. Yes, kinetic
sorry.
energy. Yeah, in all collisions, momentum is conserved, but in elastic collisions, kinetic energy is also conserved. So, for photons, when they collide with matter, the collisions are elastic in nature, which means the total energy should be conserved, right? So, as you told now, what happens to the photon after this photoelectric effect? They are absorbed by the electron. So, where goes their energy? The energy is immediately taken up by the electron and they utilize it to overcome the work function and to go out with a particular velocity. So photon collisions with matter is elastic in nature. For elastic collisions, the transfer of energy takes place instantaneously. So by the time the photon hits the electron, it comes out. There is no time lag. So this also explains why photoelectric effect is instantaneous, why there is no time lag between the fall of light and the emission of photoelectrons. So here the photoelectric effect is completely explained by Einstein's Einstein applying quantum theory. Is this part clear to you? You will also have to remember the definition of work function. What is work function? The minimum energy required to release electron from a metal plate, and it will be different for different metals. And threshold frequency is the minimum value of frequency of an incident radiation at which the electron can be emitted from a metal surface. If the incident frequency is less than the threshold frequency, no electrons will be emitted. So is this part clear to you? Can I move on?
Yes,
Can
teacher,
I?
clear.
Okay, okay. Now, this is photoelectric effect, which is a evidence that electromagnetic radiation or light have some particle nature. Now, let us see another phenomenon which also says that electromagnetic radiation have some particle nature. It's called Compton effect. Have you heard of Compton before? This is Arthur Compton, and he discovered this effect. It's called Compton effect. Now let us see what it is. When a high energy photon, not in the visible region, high energy means in the X-ray region. X-rays have more energy and more frequency than the visible light, right? So sometimes you mention the quanta of electromagnetic radiation as photon. It doesn't matter. If it is of high energy, it will be either X-ray, gamma ray, etc. Compton effect usually occurs in the X-ray region. So when a high energy photon like X-ray photon or X-ray quanta is scattered due to collision with the target, the wavelength of the scattered photon becomes larger than that of the incident photon. So here you can see a picture. Suppose this is the incident photon having a wavelength lambda I, that is wavelength of the incident photon. And suppose the target is an electron which is at rest. Now, when this incident photon, which is high energy photon, hits the target electron, what happens? It will get scattered. And when it gets scattered, when it comes out, the scattered photon have a higher wavelength than the incident one. Now, this is in the X-ray region. Just for you to understand that the wavelength is increased, the incident photon is shown with blue color and the scattered photon is shown with red color. You know that red has more wavelength than blue. It's just symbolic in nature, but actually Compton effect occurs in the X-ray region. So if there is high energy X-ray photon or X-ray quantum, which is incident on a target, it can be an electron. Here you can see the electron gets recoiled. So the electron is moving. So did the electron get the kinetic energy to move? From where did the electron get its kinetic energy to move?
Photon.
Yeah, from the photon. See, you also know the relation between wavelength and frequency, right? So the incident photon, suppose let Fi represents the frequency of the incident photon, and FF represents the frequency of the scattered photon. Which will be more? If the wavelength increases, what happens to the frequency? If the wavelength increases, what happens to the frequency? The frequency will decrease. You know, wavelength and frequency has inverse relation. If a wave has high frequency, it means it has low wavelength. Okay, so if we say that the wavelength of the incident photon increases, it means that the frequency of the incident photon must have decreased. And the energy of the photon depends upon frequency. So the energy of the incident photon must have decreased. So energy decrease means where goes the extra energy? It goes as the kinetic energy of this recoiled electron. The electron was at rest. So it takes up some energy from the incident photon and it moves. And when the some energy is lost, what happens? It will have a lesser frequency, which means a larger wavelength. So again, Compton effect can also be explained by considering these electromagnetic radiation or X-ray as a continuous, as discrete photons, not as continuous wave. So if each photon is incident on an electron, some part of the energy the electron will take as its kinetic energy and start moving, and it will scatter away the remaining photon with a lesser energy, which means a lesser frequency, which means a larger wavelength. Okay. And he,
This is the same phi, same
what?
formula, that one, the phi, the angle.
Angle. Okay, here this is not work function, this is the angle. If the incident direction is x-axis, the direction
Oh,
in which the electron moves will make a angle phi. This is not work function. Okay, this is
not
just
that formula, right?
and not from that formula. It's a totally different concept, and Compton effect was discovered independently. Photoelectric effect was discovered by Hertz and it was explained by Einstein. That's a different story. Now, Compton effect is totally different phenomena which was observed by Arthur Compton, and he found experimentally that the wavelength is increased when a photon gets scattered by matter. It can be an electron. So this is yet another totally different phenomena which also can be explained only if we consider this electromagnetic radiation consisting of individual photons or individual packets of energy. And this is called Compton's equation. Here he gives the difference in wavelength, that is final wavelength minus initial wavelength is equal to h by m0c, where m0 is the rest mass of electron. What is the rest mass of electron? What is the rest mass of electron? Mass of an electron. Do you remember the mass of an electron? It's 9.1 into 10 raised to minus 31 kilogram. So this is the rest mass. Why do we have to mention rest mass? Why not just mass? The beginning of this chapter, we were discussing relativity, right? So we know that as a particle moves with very high velocity, its mass is relative in nature. Its mass increases. Okay, so the mass of the electron, if it is moving with very high velocity, m will be equal to m naught divided by root of 1 minus v square by c square. So electron can move with velocities comparable to that of light, and it is very light. Its mass is very small. So we have to mention whenever we are talking about high energy physics or when we are talking about particles moving, light particles moving with very high velocity, we have to specify whether it is the rest mass or the mass of the particle when it is moving. So here m naught is the rest mass of an electron, which is 9.1 into 10 raised to minus 31. And h is Planck's constant. So h is equal to 6.63 into 10 raised to minus 34. And what is c? C is very familiar to you. What is c? C is the speed of light. That is 3 into 10 raised to 8 meter per second. So this whole thing, h by m naught c is a constant because h is constant, m o, which is the rest mass of electron, is constant, speed of light is constant. So all this constants value, if we substitute, we will get it as 2.43 into 10 raised to minus 12 meters. You can either remember this value, which is called the Compton wavelength, or you can substitute each of this value when you solve problems. So h by m naught c into 1 minus cos theta. Remember, here theta is the angle between the scattered photon and the direction of the initial photon. So initially the photon was moving along this x-axis in this direction, and theta is the angle between the initial direction of motion of the photon and the final direction of motion of the photon. So it is scattered from the original path. So theta. Now can you tell me any case where the difference in wavelength is just the Compton wavelength? What should be the angle then? Is there any situation when the change in wavelength is equal to the Compton wavelength? When cos theta is 0, this will become 1, right? So the difference in wavelength will be the Compton wavelength. It will be a constant. So when is cos theta 0? When is cos theta 0? Cos 90 is 0, right? So if theta is 90 degree, then the scattered wave will go like this, perpendicular to the incident wave. So you will have it as h by m naught c. So if angle is theta, then you have the difference in wavelength equal to the Compton wavelength. Now, if the angle is cos 0 is 1. So if the angle is 0, that is the initial incident photon go on without giving anything to the target. If the incident photon go on straight, which means if it is not scattered, then this will become 1 minus 1, 0. There is no change in wavelength. Initial wavelength will be equal to the final wavelength. So the incident photon will go on straight. So this equation you have to remember, which is called the Compton equation. Is this clear to you, Compton effect? Is it clear to you, Compton effect?
Yes, teacher.
Okay, thank you.